All right, here we go. What time is it now? It's about 7:01. I'd like to thank everyone for coming. I have no idea if this is actually working. If you could give me a message that says, yeah, you can hear me and everything is good, let me know here in the live chat. We'll just do an audio check here. I know that we're about 15 seconds behind, so we'll see. So I'm just waiting to see if anyone's gonna live chat in here. Send me a message. Okay, audio is good. Well, my audio levels say, well, it's a little hot actually. Let me turn this down. Okay, because I might get a little excited. So we'll let some more people sign in here. I don't know how to tell how many people I'm in. I guess I got 2 viewers on, so we'll go ahead and wait. We'll wait about 5 minutes. I'll just go ahead and tell you what I've been up to. So, you know, this year I ended up buying a lot of video equipment. So in my office here, I can do some real production. I got some lights. You know, I got a big light up here, and I got another light over here, and then I got like a teleprompter, which I have a camera behind it, so I can look in the center of it. And then I have several monitors to do a bunch of other monitoring. But I got this thing called the ATEM Mini Pro, and it's allowing me to do all this stuff, and I don't have to get my computer involved in it. So it's kind of freaky. I'm here talking to myself. Okay. So it looks like Michael Epstein wrote in, and he said, yeah, the audio is clear and the video is good. So I guess, well, we'll just wait a couple more minutes. It says I got 3 viewers on. Well, which is fine. I mean, I don't know what's gonna happen with this stream, but we'll go ahead and see. And if they all drop off, I'll just continue to talk until we get done. Yeah, it's interesting. It's like a control facility here with all the monitors and stuff. I will say that I'm gonna make one modification to my table, so I have my microphone and my camera mounted on boom arms kind of thing, and they're actually attached to the table, so when I move the table, the video shakes a lot, so I'm gonna have to fix that as well. But it's all good. Let me see here. We got well, it doesn't matter. We're gonna keep going anyway. But this is totally weird. I know I watch a lot of live streams, and I never even imagined what is on their side of it. It's like dead silent in here, but I know you guys are hearing me just fine. So I guess we'll go ahead and get started. So I was born. I don't want to go back all the way in history, but I do want to talk a little bit about before I bought that AM radio that I talked about in my introduction. So we moved from Pittsburgh, Pennsylvania, out to Los Alamos, New Mexico in 1973, and my dad used to work for. My dad's a chemist, and he got hired by the lab, Los Alamos National Lab, in Los Alamos, and so we packed up our car, and at that point there was 5 of us kids, and we had 2 cars. We had a Chrysler station wagon and a little Toyota Corolla, and we stuck everything in the moving van. And as we were driving out of Pittsburgh, my dad said, "We're never coming back to this place." So we went west, and we ended up in Los Alamos. Now, Los Alamos at that time, and this is going to be another story for one of these tech talks, is what it was like to grow up in Los Alamos, and the very short history of that town. But it was a very safe community, and let me just set the stage for you of what it was like in 1973, because I was talking to my granddaughter today, and her life is is so much different than what my life was. And I'm not talking about the events of 2020, but I'm just saying in general, we'll talk about technology back then. So our two cars that we drove out from Pittsburgh out to Los Alamos didn't have air conditioning. One of them didn't have a radio. The other one, the Chrysler, had an AM radio. Now, AM radio was like the prevalent mechanism for cars and people to get news, and everyone had an AM radio. So just for those older folks in here, let's just tell you what songs were on the AM radio back in 1973. So on the pop charts, these are counting down from 4 down to 1. So we had Crocodile Rock by Elton John, Killing Me Softly by Roberta Flack, Bad Bad Leroy Brown, and the immortal Tie a Yellow Ribbon Around the Old Oak Tree by Tony Orlando and Dawn. That was on the pop charts. That was mostly what was played on AM radio. But back in the 70s, 1973, the top 4 songs were Walk on the Wild Side by Lou Reed, and Goodbye Yellow Brick Road by Elton John as well. Knocking on Heaven's Door by Bob Dylan, and the now immortal Freebird by Lynyrd Skynyrd. So that 46 years ago, that was what was playing on the radio. Now we had AM radio, so we got pop music, and so when we drove out, we'd hear Tie a Yellow Ribbon all the time on the way out if we were actually had the AM radio on. But when there was 3 or 4 of us kids in that station wagon with my mom and my dad, it was utter mayhem for this entire road trip. But we got to Los Alamos, and back then we kind of had free reign in the town. We had bikes, and we could go anywhere on our bikes. I never had a key to my house when I was growing up, because we never locked it. And consequently we could go and do anything. And so I think about 2 years after that, sometime, I got a newspaper route delivering newspapers, and I took that money and I bought that AM radio. So technology wise, I started with that AM radio, and it was very simple, and but this one, you could run this on batteries if you wanted to. And my mom had this radio for a long time after I went to college, and she used to listen to KRS in there in Los Alamos. So what ended up happening, and because of the lab there, the access to technology was quite unique for a very small town at that time. But just take a step back about what this live stream is about. So what I want to do is kind of talk about stuff from my past, and also try to talk about something in my future as well. So my wife asked me today, she goes, "Are you going to keep this short?" And I said, no, what I want to really do is to kind of bookmark technology for this first one. So on the beginning side, I got this AM radio that I purchased in 1973. And then I'm going to talk about something I did last week for work. Now, a lot of you, I have no idea why you're here. I don't know if you're here, if you subscribe to my channel because I do this music room segment, or I do CNC work, or I do stuff with Arduinos and DIY stuff, or do I do my vacuum tube amplifier stuff. I don't know why you're subscribed. I don't even know why the people are here, and what you're actually looking for in these live streams. But if you found the very first one entertaining, that's kind of what I'm going to drive. And this may continue on in this kind of format, or it may evolve into something else. I don't know. But it is going to be based around technology, either something old or something new, something along those lines. So I'm bookmarking the entire segment of where I am right now. So I started with this AM radio, and then what I worked on last week for for my day job. And a lot of people don't really actually know what I do. For a long time, I didn't know what I did, because my career has been quite unique in the fact that all the companies that kind of hire me, they hire me specifically because I don't know anything about what they do. It's a very odd situation with my career. But what that's done for me in my career is I got to work in a lot of different industry segments, and I got exposed to a lot of different technologies. And when people would ask me what I did, really didn't have a stock answer for that. But what I'm doing eventually, after a lot of many startups I've been involved in, and kind of the terminology from the startup world, in the startup world, you get started and if you're going to do some kind of product design, most startups want to get to a point where they have this thing called an MVP, which is minimal viable product. It's something that's actually showable, either to potential customers, to investors, to future employees, and that kind of thing. So an MVP is really kind of critical in the beginning stages of any startup. And so it turns out that what I've evolved into being from all my career is that I was helping startups or very small companies develop products to the point where they have an MVP, so they can show, progress, do proof of concept, that kind of thing. So what I'm doing now, like I said in the introduction, is I work for 2 cryogenic companies, and I'm doing embedded hardware design. So typically what I'll end up doing, like, here's one of the boards that I designed for this company. And this is a circuit board, a surface mount board, and it's got a CPU over here, and this big thing here is, get this thing to focus on us. This thing here is an Altera Max 10 FPGA. It's got serial ports, it's got USB ports. It has a RS-45 port. It's got a footprint down here for a ESP8266, which is a Wi-Fi radio, and this was the proof of concept board for this idea that this company had. And with this, we were able to develop firmware for both the CPU as well as the FPGA, and got it to interface with the devices that it needed to kind of communicate with. And we were able to provide additional communication capability and take a design that was basically designed in the 80s and be able to communicate and be able to connect it up with its communication channel in with the way that things are communicated now, either over Ethernet or Wi-Fi or that type of thing. So it kind of adds some additional capabilities and kind of extends the life of some of these products that they have. It also enables them to sell new products into existing facilities to replace aging equipment. So what I do for my day job is I'm an embedded hardware designer. So what that is I'll do this board layout, and I'll get a circuit board like this, and then I'm able to kind of prototype these boards and put all these little components down with a thing called a pick and place machine, which I have some videos about that as well. And then I write the firmware here. Now I write the firmware for the CPUs, and then I have a FPGA developer in Massachusetts helping me with the code for this. And it took us about, I'd say, 9 months to get this thing working. And we ended up doing a field installation, and it went successful. But that's kind of what I end up doing now. And these 2 companies I'm working for, I have about 4 or 5 designs that are kind of at this level. And so I've been helping companies do this kind of product design. And a lot of times in my history as a career, I've been brought in to help companies in a lot of different ways. But one thing that kind of plagues a lot of small companies is that they contract out services like design services with other firms, and they go through a negotiation stage where they own the intellectual property rights, and they start producing a product that was designed by an outside firm, and that product is brought on the market, and it's sold, and it could be sold for many years. So one of these companies has a design that was designed about 10 years ago. It's a hardware design as well as some software. And that company that did the design work is kind of no longer in that business. They cannot support making changes to this product that has been marketed and sold for 10 years. And there's some bugs in that. And they would like to be able to get, they have the source code, they'd like to be able to compile it and put it onto the board and fix these bugs that have existed for 10 years that haven't really seemed to be a problem, but it's about time to actually make a revision to that. So what I'm going to talk about now is this other thing called Docker. But I want to set this in a tone that's not doesn't have anything to do with software. It's kind of more non-engineering related, more of like at the Microsoft Office kind of level of what this dilemma is. So let's say that let's say that somebody in your company from 10 years ago, let's say it's 2021. So let's say in the company's history, your all the company now all runs on Macintoshes, and then 3 years ago you weren't running Macintoshes, you were running Windows 10, okay, and then before that you're running Windows 7, and before Windows 7 you're running Windows 98. Now let's say that for some reason, a regulatory issue or a documentation revision or something along those lines, a document that was created 10 years ago needs to be revised. So let's just imagine this. You have a Macintosh. You have the document as a document from, let's say, Word from 10 years ago, and you want to revise it. But inside that document, you had back then you could create a spreadsheet and copy some cells out of the spreadsheet and paste it into Word. And then if you revise the spreadsheet, the copy was kind of dynamically linked between Word and Excel. If you changed Excel, the pasted thing inside Word would be changed, and that whole link there back in the olden days was called OLE, which is object linking and embedding. And then let's say that the data that got created from this, let's say inside the spreadsheet you also had a graph, and that graph was created with some executable from DOS. So whoever worked on that document ran this DOS program, it created a graphic, you put that into Excel, and then Excel file got saved, and then that got reflected into the final report. So you have a lot of different pieces of software along the way. And if anyone stays on at this point, you're all troopers, because this is like a crazily advanced topic we're talking about, and all these live streams they probably will not be at this level, but since I wanted to bookmark the first one, we're going to get pretty deep in here. So back to my example. So you have this exe that you ran on DOS that ran in Windows 98. You opened the version of Excel back in the 1998 time frame. You pasted it into Word, and you had Word save a binary Word file from let's say 10 years ago. All right, now you need to update it today. So how do you possibly recreate the environment that whoever created that document had 10 years ago? you'd have to find a PC and download Windows 98, and also find a version of that DOS program. And you'd also have to find a version at that time for Excel and a version for Word. So the amount of work to actually orchestrate all that and get to the point where you could recreate the environment that person that used 10 years ago, you need to recreate it today so you can revise this document and kind of create a new version of it today with 10-year-old tools. That's exactly the problem that a lot of companies have. How do we take our embedded device and make revisions to source code from 10 years ago, change that and recompile it, create a binary, and then be able to take that and flash the firmware onto the circuit board. Okay, so let's talk about this thing here. And this thing here, I have two of these designs that I can talk about, but I'm going to just talk about this one here. So this one has an enormous amount of development tools around this. You have the source code itself for the source code for the CPU, and you have the source code for the FPGA. And then you have the compilers for that code that created the binary for this. And then the source code needed a bunch of libraries, and that all has different versions. And then the same thing exists on the FPGA side. So you have the source code for the FPGA, in this case is Verilog, and then you have the compiler, the FPGA development tools that you could open the source code in and compile it and verify it and create the binary file to program the flash inside the FPGA. And so all that stuff has a specific version, and if any of those versions change, then you'll have to force. Let's say you just wanted to go in and change the text. Say your company name was different, so you wanted the banner on this thing to say, new company, and that's it. You don't want to show the old company name. The amount of effort to change the company name, it's a simple change in the source code, but if you change anything along the way, the compiler version, the library code, the source code that's in the library, the source code for the binary itself, the source code for the CPU or the FPGA or any of that, if any of it changes, there's a risk that you're going to totally break this thing and it's not going to work when you get it going. A lot of things are that fragile, so you can't really open that source code from 10 years ago and be able to get it to compile with today's tools. A lot of times it just doesn't work. And it's really risky to do that, particularly if these are, mission critical or their downtime is very expensive for the customer. It potentially affects the reputation of your company, the reputation of your product. There's a lot of things that you want to mitigate, and you don't want to do that at all. So what we're going to show you is how do we future-proof that process of making changes to the source code and being able to compile it in the future. Now this problem arose, and it's been getting worse and worse over time for me. So my primary desktop here is I run Linux Ubuntu 16.04, which is a version of Linux that came out but in 2016, and so now it is almost 5 years old, and I'd like to update that. But what's held me back is if I update that, there's going to be significant changes to a lot of things, and I may not be able to get my development environment back to be able to compile something for this board. So how do I make this possible that at any time in the future, regardless of what I'm doing, if I'm running on Linux or I run on Windows or I'm running on Macintosh, how can I take and save the tools and the environment of how I'm compiling today. So in 10 years from now, I'm able to compile the same thing that I do today, do it in 10 years. How can I do that? So this is a unique application that is a significant challenge for anyone who does this type of work. So I'm going to move over and I'm going to talk about this thing called Docker for just a minute. So Docker is a container type environment that was primarily developed for cloud computing. So let's say I'm doing some cloud app, right? And I want it to run at Amazon or over at Microsoft or some other cloud provider, IBM. So I develop on my desktop here and I get everything to work right. I want that same environment that I have on my desktop. I want to capture it and push it up to the cloud and then run it on the cloud. Now the cloud version of everything may be different than my desktop version, but I want the cloud, the software that's on the cloud infrastructure, it might be different. And so, Michael says, are these web-based codes or everything is local? Everything is local. So all my source code is actually stored here locally. Now, I do this thing called revision control and that type of thing, but we're not going to talk about that. So let's talk about why Docker was invented. So Docker was invented so I could take my environment here, capture a little piece of it, push it over to Amazon or whatever, and run it over at Amazon. But I do my development locally. But in order for Docker to work, it needed to basically run the application that I created on my desktop over there. And I don't compile it over there, I do everything over here. So the amount of energy that Docker saves in the development cycle it's mind-boggling how simple it is to get Docker to run and to do development using Docker, and I'm going to show you why that is. So Docker came out about 10 years ago, and it was just an idea back then. Like a lot of these projects, everything starts with an idea or solving a problem, and Docker grew and grew and grew in popularity. And this slide here is showing you now that the use of Docker is enormous. They have a kind of this repository thing called a Docker Hub, and since they've been running, they've had more than 242 billion pulls from Docker, the Docker Hub. So there's a lot of developers out there actually using it, and they do a pull from Docker Hub, they pull it down, they build their environment, and they push it back they push it back somewhere else. So in the past month alone, it's up to 11 billion. So what this slide is showing you is that this is a well-established technology that's going to be around for quite some time. So this massive numbers are for cloud deployment. But we're going to use Docker for a different type of environment today. So let's go back over here. So what I'm going to use Docker for is I'm going to capture my embedded development environment, and I'm going to run it in Docker. And then I can take that thing called a Docker container, and I can run it on my desktop here. I can run it on my future desktops, but be able to open up the environment from the past. So when I update my desktop, I can fire up a Docker container and compile everything like I'm doing exactly today. I can take that Docker container and I can run it on my Linux desktop. I can take it and run it on my Windows desktop. So that's kind of what I'd like to show you, if I can get this to work. So if anyone is on at this point, I'm just really surprised. Okay, so I'm going to go over here. Linux computers require that you name something. So I have the command shell launched in this other window. So here's my shell, And this computer that I'm on now is called Hendrix. So what I'm going to do is I'm going to go into this dev environment directory. So this is where I have all my source code. So, and all the tools to compile the source code. So for this particular project, I'm using the Arduino libraries to set up a bunch of things inside the microprocessor. And then I wrote a bunch of C++ code that uses the C++ compiler that's provided by the Arduino development environment. But I'm going to do everything without using Windows, like Windows per se. I'm going to use the command line to actually compile this environment. So I'm getting some kind of warning here on the stream. All right, so this is the directory that I can make this version. And if this is totally over your head, you got to drop out. I totally understand. But this thing I'm going to work on today, this is the source code, and this for this kind of board here. So the firmware that runs on this board is in here, and then this thing also runs at HMI, which is a human machine interface. And so I'm going to compile the firmware. The firmware is what goes in the microprocessor. So we're going to go into firmware, and then what I've done is I've captured the source code. I captured it when on 12/31 of last year. I captured the source code for this project, and then inside of here is the source code. So this is all the source code to generate the compiled version for this thing here. So if we go back up here a couple of directories, so there's some additional files in here, and there's this thing called a Docker file, which are the instructions for Docker to build this container. And it copies my source code over to the container, and it also copies all the development tools to the container. And then it's going to go ahead and run the container. So I'm gonna look at my cheat file here, which is called a make file. And the first thing I'm going to do is build a Docker container. So what it's doing is it's downloading Ubuntu for the version that I have on my desktop currently, which is 16.04, and it's going to download a bunch of binaries and get the operating system ready to. It's going to get the operating system installed into the Docker container. And now you might think, what's the difference between Docker and something like Vmware? Well, this Docker container I can launch in about a half a second. You'll see here in just a minute. So what this is doing now is it's like updating. Like on if you're familiar with Windows or Macintosh or something, you go and you want to do a system update, and it downloads a bunch of stuff, and it installs a bunch of things. But what this was doing is it's actually installing stuff on the container, not on my desktop. So everything I'm doing now is not affecting my desktop at all. So now it's going to take the this thing called STM32Arduino, which is the Arduino development that is actually running a thing called the cross compiler. So I'm actually compiling ARM code for this microprocessor. So I have to have a cross compiler. So I have the source code, I have a cross compiler that compiles the code for a different microprocessor. So it's almost like on Windows I'm compiling code that will run on a Macintosh, but in the embedded world it's about doing the I'm going to be on Linux, and I'm compiling code for an ARM processor that's different. So that's what a cross compiler is. So what this is doing, it's copying about a gigabyte of data into the container. Okay, so it did that. Now it's copying some more stuff, and it's setting up my environment. So now it's ready to run. Okay, so now the container is ready to go. So I'm going to run the container. So if I look at my make file again, we have this command right here. So right now, when the prompt changed over here from Holla at Hendrix to root at this crazy number, now I'm actually typing commands into the container. So none of this is. It's almost like I'm logged into a completely different computer. And you saw how fast it booted. Like I'm running a small version of Linux on top of my Linux machine, but I was able to boot the small version in a half a second. That's one of the big powers of Docker, is that it launches incredibly fast. So over here, if we look at this, at the directory, I have the Arduino environment installed, and I also have my source files. So in source, I have the firmware and the HMI. And so we're going to go into the HMI directory, and now we're going to compile the source code. So I use this thing called make, which runs the compiler, and you're going to see a bunch of stuff like in Matrix come up. Except that's not right. There's no make file here. Oh, I got to go into this directory because this is the capture of the source code at that date and time. So now I'm going to make the source code. So here's the compiler going through and compiling all my source code. And now it's done. Okay, so let's say I wanted to change something in that firmware. I could go in and edit this stuff, run make, compile it again, and then flash my board. And that's really all it takes. So I can also flash my board from here. So I have an embedded device here on my bench, and I can actually flash it. So we're going to do this thing called make flash, and it's going to run my flash routine. And now I've installed the newest version of the source code onto my embedded device. All right, so let us review. So we're going to log out of the Docker environment and go back to my Linux host. Okay, so now I'm back at Hendrix. That Docker container is still there, but it's stopped. And let's say I want to start it again. Well, I can just say, and look at my cheat file again and say, Docker start my environment again. Okay, so now it's running, but I'm not attached to it yet. This is a little aspect of Docker. So it's running on my computer. It's just sitting there waiting for me to actually kind of effectively log into it. So now I can attach to it. And now I'm back in my environment. So that's how fast it took to boot up. And when I'm done, I can exit out of that and I go back to my desktop. So that's we'll get a question in from Michael. So it says, and Docker saves and stores this operating environment for future recall. That's exactly the whole point of all this. It's to say in 10 years from now, this company comes back to me and says, we need you to do some work for us again. And I say, okay. I bring up this Docker environment in 2030. I can bring up this entire environment then in 2030 and be able to compile it like I'm doing today with the exact same tools. Everything is the same as what I'm currently doing today. And you saw how fast it run. And if computers run if the acceleration of computer technology is anywhere near what it's been in the last 10 years, it's going to compile it in probably, I don't know, half a second. I don't know. It's hard to envision what's going to come in the future. But that's the point of that. So now what I'm going to do is I'm going to reboot my computer. I don't have to stop the live stream. I'm going to reboot my computer into Windows, and I'm going to bring up a Windows command shell over here, and I'm going to do the exact same thing over here. All right, so let me quit out of all this stuff and get rebooted, and hopefully we don't lose our live stream. So I'm going to reboot this thing and cross my fingers that it boots up in Windows. So Yeah, it. I've never actually seen or heard of using Docker in this kind of fashion, but its capabilities make it so I don't have to worry about actually ever. I don't have to worry about ever being able to compile this, being able to recreate the environment I have today to compile this source code. I can do it whenever. And this whole idea of this Docker will run on a Macintosh, it'll run on Windows, and it'll run in Linux as well. Now, I don't have a Mac here, but I'd like to try that out. I might have somebody else try that on theirs. But that's the promise of Docker is to do this very thing, because what it ends up doing is on Linux, on Windows, and on Macintosh, it actually runs this tiny version of Linux inside the Docker container. So it's always Linux on whatever the host platform is. That's where its power comes from. And if I decide that I don't actually want to use a computer, I can launch an instance at Amazon and get the Docker environment installed at Amazon and just do all this in Amazon. I don't even need a desktop. Okay, so what we're going to do over here is I am running I'm running this thing called Docker Desktop. And that's how I'm running Docker on the desktop. But let's... Uh-oh. It says it wasn't able to launch Docker. That is not good. Maybe Docker hadn't started yet. Okay, we're going to go over here. All right, so now I'm back. I've booted up Windows, and I've run this ancient way of running programs on Windows machines. Because before Windows, yes, there was a time in the past that Windows did not exist. Before Windows, there was a thing called DOS, which stands for Disk Operating System, and this is what originally came with the IBM PC in 1981. Was this thing called DOS, and it was all command driven. It all looked like this, and people learned these cryptic commands to do all this type of thing, and so it's the equivalent. Basically, this command shell runs exactly the way it did in 1981. So how many years is that? I don't know how much. 37 years. I'm using the same technology that was. But I'm able to. I'm just typing in raw commands this way. I don't have a GUI or anything, so it's very similar to the way I was running it on Linux and Windows the same way. And this command shell CMD will kind of always work in future version of Windows, because the way that Windows operating system runs, it does a lot of things through executing commands in the background. Behind the scenes, behind the window itself, it's running DOS commands. Now, since I grew up in New Mexico, we didn't pronounce it DOS. We pronounced it DOS. Uno, dos, tres, cuatro. But I digress. All right, so here, this is where it gets kind of odd, and you got to not only kind of understand what I'm talking about, but on the Linux side, different commands, and on the Windows side. So for me as a developer, it's almost like I have to speak French and German at the same time. So, because running the DOS commands is one language, basically, and running Linux is a different language. But here's our environment, okay? And we see that we have this is not our environment. This is our, oh, come on. We got to go up one. And we got to go into the temp directory. I put everything in the temp directory for today. All right, so here's our directory. Now, these files look really similar to what these are the exact same files that I had over on the Linux side. We have this thing called a Docker file, and I can actually show you the Docker file here. I think. Let me see. What's the command? Is it more on the DOS? Oh yeah, there we go. So this Docker file is a instruction for Docker to actually create the container. All right, and we have a make file here as well. But this make file actually runs on the Linux side. Okay. But these are the commands, these are the exact same commands we need to run on the Windows side. But I don't have make installed on Windows. I have to type these commands in individually. So to save time here, I created a Windows directory here. And if we look at what's in here, we have a bunch of .bat, they're called batch files. So these are our commands that when I run a batch file, it actually effectively types in commands into the command line. So if I look at one of these things called build, okay, build is just a command that says docker build minus tag and dev environment ... All right. So if I run this, what this is going to do is it's going to create my Docker environment. So let's go ahead and do that here. So we're just going to do that. And what that's going to do is it's going to go download Docker, and it's done. Okay, so there's some cache advantages to running this on Windows. This operation on Linux side took about a minute, but over here you saw it was almost instantaneous. And I think that's the way that Docker kind of does some caching mechanism to be able to build these containers really quickly. All right, so there's another bat file in here called run. So we've created the container, but we need to run it. So we're going to go ahead and run this one here. Okay, so now we're running it, and so now we're back to that root prompt, and it's got some crazy number on it. But if we now we're on Windows, but we've booted a Linux container in Docker. So effectively, we're logged into a very small version of Linux on Windows. So now I'm going to switch languages. I'm going to talk on the Linux side. So there's my Arduino development environment directories. And here's my source. And here's firmware and HMI. And if we CD into HMI, we have our source there itself. So here's our source. That was the same source that we were showing you on the Linux side. And I can type in make. And now I'm cross-compiling. Inside Docker, I'm running a version of Linux, and I'm cross-compiling the source code for an ARM processor, and all that's running on a Windows host. Yeah, no, this is really kind of mind-boggling, all the different layers. But I'm going to bring up another command window, and I'm going to CD into the right directory. Okay, so I have two windows going. I have this one here, which is on the Windows side, and this one over here, which is on the Linux side. So if we look at the things again, I have another command called flash. And what that's going to do is it's going to copy the binary out of my Linux container onto the Windows side, and it's going to run a Windows version of the flash routine and program my firmware. That is not good. That is not good. We're live, baby. No. This is not good. Oh, wait. No. Well, that's unfortunate. I checked everything earlier. Hold on a minute. Well, crap. I don't know what happened here. It's the problem with live demos. Oh, I know what happened. Okay. Yeah. Need to plug in my USB hub. All right, here we go. Let's do it again. Dun, dun, dun. All right, there we go. We're flashing our firmware. Okay, so let me. If you know, let me go ahead and reboot here so I can get back to my YouTube Creator Studio going again. But I'm going to reboot into Linux, and I can make sure everything's working right, because I'm not seeing anything because I've rebooted my entire desktop. So I don't know what the live chat's been going on. I don't know anything, but I'm going to go ahead and get this booted up again. And we will go ahead and summarize what kind of crazy stuff you saw this evening. And for those of you who do any kind of development like this, I will go through and do this example again and gear it really towards, you know, kind of embedded developers, because I don't want people to kind of chime into this. This one's pretty informal, as you can tell. But I will plan on doing this one again because it's a really important. Well, I think it's an important topic for future-proofing all your embedded development work. And I haven't, like I said before, I haven't seen this thing used this way. So let me get, okay, I'm booted up in Windows. Let me get my YouTube going here. We will see if there's any other chats going on here, and I'll answer any kind of questions after I kind of summarize things. Come on, YouTube. Here we go. Go over here. I don't know how to get back to my channel here. We're streaming now. Okay, I'm back in my channel. All right, here we go. So let me just summarize. So what I've been able to do is use Docker, which is a technology that was originally developed to deploy apps into the cloud. And I was able to take advantage of Docker's cross-platform of compatibility. So if you have a Docker container on Windows, you have a Docker you can run it on Linux, or you can run it on a Macintosh. Inside my Docker container, I saved all the development tools to cross-compile my embedded firmware inside the container. Then I built the container on both Windows and on Linux, and I was able to compile the source code using the tools that are currently used right now. And I was also able to flash the firmware onto my embedded device. What that's going to enable me to do is, with those files in that one directory, I can recreate this environment at any time in the future, as long as Docker is available. And it doesn't matter what versions of anything I'm doing. So now I'm free to update my desktop. I'm free to run newer versions of Windows. And Windows, update procedures were not going to break my development environment. I can freely develop in a more less restricted mode, because I know that I can always fire up everything that I have right now and be able to compile this firmware. And from a development standpoint, I've never been in this situation before. A customer might come to me 2 years from now, or they might come to me 10 years from now and say, can you build us? Can you make some changes for us? And my customers that I've had over the last 40, I don't even know how long, I graduated 30 years ago. And a lot of them come back to me and they want me to continue doing the same kind of development work for them. And there's one more example of this, because I know that I'm at the hour point. One of the projects I worked on ran in Flash, And Flash is a browser-based technology that was originally invented by Micromedia, and then Adobe bought it. And Flash ran in a lot of browsers, and it ran for a really long time. And a lot of developers hated Flash. A lot of people hated Flash, but I did it in Flash, and it ran one of these embedded systems because I could run it on Linux and get and do some really creative things with that Flash technology. And that customer continued to make changes to that for about 3 years, and so I had to make sure that whatever I did to my desktop, I was able to bring up the Flash compiler tools and be able to make changes for his needs. And so I know that that's going to be the case. I know that I'm going to be doing this type of work, and this is how I'm going to move forward from now on. I'm not going to install tools specifically on my desktop. I'm going to install them in a Docker container solely, and as the Docker container, it matures, I can persist the container and say, this is how I did this. Store that off. And I can have another container for some other compiler or technology I'm using, and another container for something else. And I'm going to be able to future-proof all my development work from here on out. All right, so let me see the questions here. We have Full Wave Wrecked comes in and was cave diving back in the 80s and 90s. So he's fine going down a rabbit hole. I haven't been watching this, as you could tell. It was enough to kind of coordinate all the stuff I had to do just to get my demo to work. I guess and then there's somebody, Rob R. I guess that's a friend of mine. So I don't know how many people watch this. The average watch time was 8 minutes. I guess it was boring. That's fine. Okay, so like I said, I needed to bookmark this. So started technology and buying a radio in 1974. Last week, I figured out how to use Docker to basically do my embedded development work and be able to future-proof all my designs, all my design work. So that's pretty much bookmarks things. Now, where is it going to evolve from here? Where is this Tech Talk with Grandpa going to evolve to? I don't really know. I'd like to get some people. I'd like to kind of do some interviews on here, if I can kind of talk someone into doing it, and just kind of tell some old stories and kind of talk about technology of today. So if you made it this far, I'd like to thank you, and we'll see you next time on Tech Talk for Grandpa. Okay, have a good evening.